Welcome to homework.
Okay, so this is problem 24.59. And this problem we have a normal microsomerly interferometer, and in one of the arms we actually inserted a glass container, which is like this, okay? And the width of this glass is D, which is 1.155 centimeters, okay? And then we started to fill this glass with gas, okay? So gas is going in there, and this gas will, the new medium here will definitely have the refractive index, okay? And this is what we are actually solving for. And after the container of glass we observe is filled with this gas, we observed that actually there were 158 bright fringes that were observed for a wavelength of 632.8 nanometers, okay? So the question is asking what should be the refractive index of uh, this gas, okay? So actually the two arms, the light going through the two arms should have the same distance, but now because of this refractive index, okay, actually there should be an effective distance, okay, that actually is different than D, because light is going to travel slower inside this medium than it's going to travel through air here and here, okay. That's why it will take more time, and as if it actually traveled for a larger distance than D, so that we will observe this interference pattern here, okay. So in order to get a feeling or an estimation of this effective distance, we can try to figure out what should be D inside this container. So D will be just the velocity of light inside the container times the time it takes to travel through the container. Okay, and V here is just C over N, where c is 3 times 10 power 8, which is the speed of light in air, okay, or in vacuum, times t. So we can get n to the other side. So nd is equal to ct. And actually ct is the distance that the light wave will travel if we don't have this new medium with this refractive index. So actually the distance here, the effective distance, um, that traveled by the light inside the container is nd. And so we are requiring that the path difference, which is we can call delta x, okay, over n should be equal to our lambda, right? And delta x here is just nd minus what is traveled by the other arm, by the light going through the other arm of the interferometer, which is just d during the same time, okay? And this is just n minus 1 times d. So we can go back here and substitute. And actually, yeah, delta x should actually be twice this quantity here, because the light wave is going forward and then it's going to reflect backward here. So it should be multiplied by 2. And so we can go back and substitute here. So lambda is equal to 2 times n minus 1 times d over big N. And so n minus 1 is n lambda over 2d, okay, which we can solve. So n is 158 times lambda, which is 632.8 times 10 to the minus 9 over 2 times d, which is 1.155 times 10 power minus 2. And this will give us, so n minus 1 is 1.004 328 And so, oh, sorry, it's just O without 1. And so n itself would be 1.004328. And so this will be the refractive index of the gas. So the main idea here is actually the path, the optical path of the beam of light going through this container of gas is actually not the same as the other beam going through the other arm, which is just a vacuum, and it will go through an effective distance, which is just nd, and so the path difference would be nd minus d multiplied by 2 to actually account for the fact that the light is going forward and backward after getting reflected from the mirror. Uh, and then lambda is just the path difference over the number of fringes, and then we can get the value of n, which is 1.004328.